Alright class, in this video we're going to talk about exponential growth problems, and we are going to use the model P of t equals P0 e to the kt. We're not going to use a times b to the x because we're not expecting a and b to be integers. So we need to use this model, we should use this model, there's lots of reasons to use this model, and this is what is to be expected of you. So don't use any other model. Alright, hopefully that's clear now. So here's the problem we're going to deal with. I actually looked these the data numbers up. So the population of Cary was 27,000 in 1980 and 97,000 in the year 2000. So we're going to write an exponential function that models the population at any time t in years. Now, for ones like this, we're not going to use the numbers 1980 and the numbers 2000. So we're going to let t equal 0 be synonymous with 1980, and therefore t equals 20 would be synonymous with 2000. Okay? So, the initial population they gave us, in this case now, is 27,000. So we know if we're using our model, P of t equals P0 e to the kt, we know that P0 is going to automatically be 27,000. Alright. So using the other data point, 97,000 in the year 2000, so that's when t equals 20. So 97,000, that's what P of t is. So I'm basically just taking the P of t and replacing it with 97,000. That's equal to 27,000 e to the 20k, because we know t equals 20. Alright, so we're going to solve for k. That means we're going to divide by 27,000. And so we got 97,000 divided by 27,000. And then we'll do a little trick here. So that's e to the 20k. Notice we can chop the zeros off. Okay. We want to undo the exponential function, so we take the natural log. So we get that the natural log of 97 over 27 is equal to 20k. And that means that k is equal to the natural log of 97 over 27 whole thing divided by 20. Make sure when you enter in the calculator you enter it in like that. Okay? And, whoops, let me let you see that. So then I did that on the calculator and I got 0.064. Okay? So I'm going to use 3 decimal places. I will say, well, we'll get to decay for the next video, so I'll save my comment for that. So the question was to write the equation, and we haven't done that yet. So there's our equation right there. Okay? Now we might have another part to this, so let me just say what will the population be in 2020. Now, you could make a guess at this. You probably have an idea of what the population of Cary is currently. If you look up the data, you probably see estimates. We're going to go ahead and use our model, and then we'll talk about it. Okay? So this would be P of 20. Sorry, P of 40. 40. All right, and that's going to be equal to 27,000 e to the 40 times 0.064, so that's the k and the t. And you can just punch this in on the calculator, and I got 349,267. I rounded it to the nearest number, whole number there. That's not very reasonable, and we should understand that. Okay, so this is what we call extrapolation. And when you extrapolate with an exponential model too far past the data, you get ridiculous answers like this. So note that probably there's going to be limiting factors. Between 1980 and 2000, they annexed a lot of land, which they don't have any room to do that anymore, so they're not growing as fast. So keep that in mind when you're using a model like this. Okay? We might also have a question. When will the population be let's say 200,000. Let's say right now the city of Cary, North Carolina, has a population that, you know, basically, well, just let's say it this way. Let's say they have a water treatment plant and it can handle a population of 150,000 or up to 200,000. So they want to be able to plan an expansion on that water plant or something like that when they get close to 200,000. And they don't want it to be 200,000 before they do it. They want to, you know, sort of expand it before then. So they need to, you know, be able to use something like this in city planning. All right, so here's how we're going to solve that. We're going to take our model right there, and we're going to place the P of t with 200,000, and then we're going to solve for t. Okay, so 200,000 equals 27,000 e to the 0.064 t. And we just solved something like, so the solving looks just like this, okay? So we just solved one. So to save a little bit of time, we're going to divide by 27,000, chop off some zeros, and take a natural log. So we're going to get natural log of 200 over 27. That's going to equal e to the, no, sorry, not e, 0.064 t, and then we divide by that, and we have our estimate. So time is approximately natural log of 200 over 27 divided by 0.064, and I did that on my handy dandy fancy schmancy calculator, and I got 31.289, and this is years. Okay, so what's the answer to my question? When? Well, 31 doesn't really make sense in the context of the problem, so you have to add it to whatever time was equal to 0, which is 1980. So our answer would be roughly 2011. Okay, so I like to pick on Cary because, you know, it's a bad place and we shouldn't want to live there. But in addition to that, what I would say, the growth rate for a city that basically can keep up with infrastructure to support such a growth rate normally is around 2%. So this is like 6%. So this is way over what the city can do to manage that. And if you know people that were annexed by Cary that didn't want to be annexed by Cary, it can be particularly expensive because the city will annex your property and force you to put in sewer lines and things like that because the city can't afford to do it. So when they do that, that can, you know, you can sort of have to pay an extra $30,000, and that's a big thing to think about. All right, toodles.